Well, I guess I'll get started here. Let me begin with a word of prayer. Oops. Dear Father, we thank you for this day again. I thank you for this class and this time we have to meet together and study your creation. I just pray that you be glorified at what we do, and that we all understand a little bit more about the non-homogeneous problem today, Lord. In your name I pray, Lord Jesus. Amen. So, before I even get into the non-homogeneous problem, I should take another stab at the homogeneous problem just a little bit. There is another way to think about it. So like last time, I emphasized that we could solve the problem. Like last time, we were basically what? We were given L is equal to some polynomial in the differentiation operator, right? So like an d to the n plus dot 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 plus a2d squared plus a1d plus a naught, where a0 through an were real numbers, and a sub n, of course, is not equal to 0, right? So as I discussed with you guys, we can solve this problem by factorizing the operator, right? And this does present some temptations which are to be avoided. So let me give you a cautionary example. Suppose I have d squared minus 3d, we'll say plus 2, acting on y equals to 0, all right? I might write something like this. I might say, oh, well, d squared minus 3d plus 2 is d minus 1 times d minus 2, right? So far, so good. No problems here. And I might then say, I'll write the offensive part in red. I might say, oh, this equals to 0. So that tells me that d equals to 1 or d equals to 2. Therefore, I get like y1 is e to the x and y2 is e to the 2x. See this? Everything I just wrote in red, I must not write, because this is complete and total nonsense. The differentiation operator is not equal to 1. The differentiation operator is not equal to 2. Neither of these things are reasonable. And of course, the idea that d minus 1 times d minus 2 equal to 0, that's equally ridiculous, right? None of these things are true. This y here is important, right? And there's a theory that we used that said, well, if this is the case and that factors like that, that then implies that, like from this, I can go straight to that. That's fine, that's true. But I cannot write this here, because that is not true. We cannot say an operator is equal to 1 or an operator is equal to 2. Unless we're talking about the constant operator, just multiplication by 1 or multiplication by 2, right? That would be okay, but that's not what we're talking about. So there is another notation. Here's a theorem. A polynomial in the differentiation operator acting on e to the lambda x is equal to, check this out, the same polynomial of lambda times e to the lambda x. Thus, p of d acting on e to the lambda x equals to 0 is true if and only if p of lambda is actually equal to 0. So I can trade my polynomial in the differentiation operator for a corresponding polynomial in lambda, right? And so I could write things like, going back to my example 1, here's another take on example 1. Example 1. So I've got my d squared minus 3d plus 2, right? Acting on y equals to 0. I take that and I write down lambda squared minus 3 lambda plus 2 equals to 0. This is the so-called characteristic equation of the problem, all right? This is the characteristic equation. And this I can factor, you know? lambda minus 1, lambda minus 2 equals to 0. And now I'm completely within my rights to write, therefore, lambda equals to 1, or lambda equals to 2. Hence, y1 is e to the x, and my other solution, y2, is e to the 2x. Completely logical, completely fine. These might seem like the same thing to you, but they're not. Right? I can say a constant scalar variable is equal to 1 or 2. I cannot say the differentiation operator is equal to 1 or 2. Are these related? Absolutely. Are they the same? Nope. No, they're not. Okay, so if you want to do polynomial algebra where you're, identifying factors with zeros, you need to use polynomial with a polynomial variable. Here's another example. So suppose we're up against like y prime 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 plus 4y prime plus 5y prime prime plus 5y prime equals to 0. All right? If I wanted to write down the characteristic equation for this problem, what would it be? What's the characteristic equation? What was that? I didn't quite hear you. Lambda cubed. Very good. Yeah. So let's see here. This is the characteristic equation. So I just need to clarify some language here. This is the characteristic equation. What's the characteristic polynomial? Let me call it P of t. What would P of t for the variable this time rather than lambda? What would that be? T, yeah, t. Well, you got t cubed. Cool. Not equals to 0 though. It's not an equation. It is an expression, a polynomial, if you like. All right. So this is just, some language to be careful about. There's a difference between a polynomial and an equation, right? We factor a polynomial, we solve an equation, right? These are connected but different ideas. Of course, if you factor a polynomial, it's very simple to know how to solve the corresponding equation, right? Factor this polynomial, how's that go? Well, t squared plus 4t plus 5. Complete the square on that thing. I've got t plus 2, quantity squared, plus 1, right? So if I look at, if I set this equal to 0, then let me flip back to lambda here. So in other words, the same thing's true for lambda, right? I've got lambda times lambda squared, it's going to be lambda plus 2 squared plus 1 equals to 0, right? That's my characteristic equation. What are my solutions? Well, my solutions are lambda equals 0, or negative 2 plus or minus what? We have a square plus a number. Remember, this is a complex case, right? So I have a complex root, pair of conjugate roots, minus 2 plus or minus I here. So in short, to solve the problem, y is equal to c1 plus c2 e to the minus 2x cosine x plus c3 e to the minus 2x sine of x, right? All right. So I wanted to mention this because if you read the book, so by the way, where am I in the book? If you were to read Nagel, Saff, and Snyder, which would be difficult because apparently we haven't given you an access code, also none of you care. Although you did pay $30 for it, so that's kind of not cool that we haven't given you a code for a book that you paid for, apparently. Sorry about that. Apparently we have like a open access something or other, and you're supposed to all have a book. But I don't know. I think Dr. Wang has the code now. We're still in the process of trying to get the code so you guys can look at the ebook or something. But as you know, I've provided you notes which are probably more relevant for my course. I mean, it's nice to have the book, don't get me wrong. Once you do get that book, we're basically covering chapters 4 and 6 at the same time. So chapter 4 is the n equals 2 case. Chapter 6 is the nth order case. I just cover nth order, and n equals 2 appears as a subcase because the method is general. So there's really nothing to be gained by just doing n equals 2 separately. Anyway, just a side comment there. I wanted to mention this idea about characteristic equation to you because this gives us an alternative way. If we don't want to factor polynomials, we can also, if we don't want to factor an operator, we can also factor the characteristic equation using ordinary laws of algebra and such, all right? But keeping in mind, we know what the deal is. If we have real roots, I mean, we get e to the lambda x is my solution, right? If you have a complex root, you have to use the alpha plus I beta thing we talked about last class, and that gives you, e to the alpha x cosine beta x and e to the alpha x sine beta x, one for each root. Great. So with that settled, hopefully, and we keep using, by the way, part of the reason I have adopted the operator approach primarily is we're going to use it today to understand how to solve the non-homogeneous problem. All right, we're going to use it to understand that. So let me give you a typical warm-up example here. Suppose you wanted to solve y prime prime plus 3y prime equals to, I don't know, let's say e to the 2t. All right, we'd like to solve. We haven't done anything like this yet because this is a non-homogeneous problem. All right. Now, so here's the deal. I look at this and I go, okay, well, I've got lambda squared plus 3 lambda, which is lambda times lambda plus 3 equals to 0, which tells me that I've got like lambda 1 is 0, lambda 2 is minus 3. Therefore, what I'll call the homogeneous solution, I can write as C1 plus C2 e to the minus 3x. Oh, but I shouldn't write x here. Why? T is the independent variable, right? So I don't write x here, I write t. All right. So this is the homogeneous solution. What does it solve? It solves, it satisfies the following equation. It solves yh prime prime plus 3yh prime equals to what? 0, right? It's a solution to the homogeneous equation. So you've probably forgotten, but like 2 classes ago, we talked about the general theory, right? And the general theory said that for a non-homogeneous problem, you have to find a homogeneous solution, and you have to find a particular solution. The homogeneous solution is not actually a solution to the given non-homogeneous problem. It's a solution to the corresponding homogeneous equation. So we got that piece. Then the other thing we need is a quote-unquote particular solution. So the particular solution is an honest-to-goodness solution to the problem we're looking at. Let me write down what we need. We use y sub p for the particular. So we need y sub p prime prime plus 3y sub p prime equals e to the 2t, right? So the question is, how do we find such a function? Any ideas?
We can subtract e to the 2t and set it all equal to 0.
Subtract e to, set all equal to 0, then what?
We can change the domain to t.
Change the domain to t. But I'd still have like a yp prime prime and a yp prime, and I'm trying to find yp, right? Could you guys, how about this? Could you guys make a guess? What would the form of the solution look like here? How about this? Let me put something in your mind. Would an exponential like e to the 2t work? What if I take e to the 2t and I differentiate twice? What kind of function do I get? I think I get 4 times e to the 2t again, right? What if I take one derivative? I get an e to the 2t back again, right? So think about it. If I put a function of the form e to the 2t as my particular solution, that should work. I don't know how many of them I need, but check this out. If I put yp equal to an undetermined coefficient, so this is the so-called undetermined coefficient right here. It's currently undetermined. It won't stay that way. So what I'm telling you guys right now is the so-called method of undetermined coefficients. So this a is a number we don't yet know. Let's figure out how to know it. What do we need to do is to plug it into the differential equation. What happens? So plug that in up here, we get yp prime prime plus 3yp prime is actually going to give me what? I get 4 a e to the 2t, right? Plus 3 times 2 a to the 2t equal to, well, e to the 2t. Can we solve this equation? Does it work? How many? We got what? 10? Yeah? 10a e to the 2t equals e to the 2t. Let's cancel the e to the 2t's. We get a equals to 1/10. So what's my solution? Therefore, here we go. We have now solved the problem. Y is equal to, so what we do is we do the homogeneous plus the particular. That's how to find the general solution in the non-homogeneous case. And so we got C1 plus C2 e to the minus 3t plus 1/10 e to the 2t. And there you go. That's the solution. All right? Right there. We solved it. This is our first non-homogeneous. Are you happy? You should be happy. We solved the non-homogeneous problem. This is an accomplishment. You should all be very happy. Let's try to solve another. So what's the method? Let me describe the method to you.
Find the homogeneous solution and then find the particular solution.
Yeah, 1, find the homogeneous solution. 2, find the particular solution. 3,
Put it together.
yeah, y is equal to yh plus yp solves L of y equals to f. So here we have L of yh equals to 0, and here we need L of yp actually gives us back the f again, all right? So just to give you a breakdown on the method, number 1 we talked about last class. Number 1, last time, I gave method. Or you could go my first 2 examples today, right? We could use the characteristic polynomial idea to find it, all right? Step number 2, find yp. This is what we're talking about right now. How do we do that? So what I've done so far is I showed the naive guess method. All right? We're going to do a better way right after this, but first I need to show you why it's called the naive guess method. If it's a naive guess, it must mean that this naive guess fails in other contexts. But I suppose I probably should do another successful naive guess method before we get to the more sophisticated thing, because the naive guess method does work often. So how about this? What if I wanted to solve y prime prime plus y equals to, let's say, t squared plus 3? Can we solve this? So I'll start you out. This gives me lambda squared plus 1 equals to 0. So lambda is plus or minus I, which tells me that my homogeneous solution should have the form C1 cosine t plus c2 sine t. It seems like we're working in independent variable t today. I was all in x last time. You must be flexible in changing the independent variable. This is part of the course, recognizing what the independent variable is. It's kind of a small thing, but it is a thing. And I do great on it. All right. If you write t where there should be an x or an x where there should be a t, I will take points off. Not a lot, but enough for you to notice that that's something you need to change. Okay, so then, great, I found the homogeneous solution. Yay. How should I find the particular solution here? What should my naive guess be in this context? You guys gonna make me do all the work?
T squared plus 3, so you have minus squared plus 1 equals 0.
Uh-huh.
And to set it equal, you want to have like the same form.
Yeah, I want to guess a function which is kind of the same general form as the inhomogeneous term, as the f here, right? F is t squared plus 3. This is the f. Yeah. T squared plus 3. See, but over here, you notice I had to put an undetermined coefficient in because I don't know how many copies of it I need, right? So I like your t squared plus 3, but I'm going to trade you an a times t squared plus 3. Not plus 3 either, because I don't know how many. And if I just did, think about this, if I just did with just a constant, that wouldn't work either. I really need to include a, b, and c like this, because if you think about twice differentiating and adding it to itself, you could have an intertwangling of like t squared and t and the constant. It's all there. But if you think about differentiating a function like that, that's all the kinds of things you get. All right? So this is the naive guess. To summarize, the naive guess method, you take f, take a couple derivatives of it, whatever kinds of functions that appear, you take a linear combination of those with undetermined coefficients, and you figure out what those, you then plug it into the differential equation and determine the coefficients, and that solves it. So you guys, what's the next step here then? Now that we've made our quote-unquote naive guess. What's yp prime? You said yp prime was what? I heard a 2at plus b. And what's yp prime prime? 2a. Great. So we put those together, and we've got 2a plus at squared plus bt plus c is equal to t squared plus 3. All right? If our guess is reasonable, we can solve these equations to find values for the undetermined coefficients a, b, and c. Can you do that? What are a, b, and c here? I'll start us out here. We're going to look at number 1, we'll look at t, we'll look at t squared. On the one hand, I've got 2a plus c equals to 3. My t equation, I've got b is equal to 0. My t squared equation, I've got a is equal to 1. So what am I doing? What am I doing? I'm equating coefficients, right? My constant terms are 2a and c. See that? Are there any other constants here? Nope. And this is just 3, so that's why I have this equation, right? I don't know if you can see it or not, but if you look very carefully, you can see a plus 0 times t here, right? And that's why there's this is equal to that, which is why I have this equation. All right, so we equate coefficients. Can you solve them then? Well, I'll tell you a is equal to 1 and b is equal to 0. You guys figure out c. What's c? Yeah, 3 minus 2a, 3 minus 2, which is 1. Okay, so therefore, y sub p apparently is t squared plus 1. And it turns out you guys got lucky. If we hadn't put in the bt term, you probably would have thought you're fine. It would have worked out this time, right? If you had just assumed that you didn't need the bt term, you'd have got lucky. This time it would have worked. But that's just a quirk of this example. If I throw in like a let's see here. If I get rid of, well, if I throw in like a plus t here, anyway. In an abundance of caution, you should include that term. All right, so the solution then is as follows. C1 cos t plus C2 sine t plus t squared plus 1. So this is called the method of undetermined coefficients. But you should understand that when we complete the method, there are no coefficients left, right? Except what? Except the constants which form the homogeneous solution. And we can't get rid of those unless what? Unless initial values are given. Like if I tell you the initial position, initial velocity, then that data will fix the values of C1 and C2. All right? So like if I told you additionally, by the way, y of 0 is equal to 0, and y prime of 0, I'll give you your 2, is 2. All right? Then that gives me 0 is equal to C1 times cosine of 0, which is 1, plus 1. And 2 is equal to C2 times the, so like when I differentiate, I get a sine here and a cosine here, so when I, I'm sorry, let me just differentiate so you guys know what I'm doing. Y prime is minus C1 sine t plus C2 cos t. I'm trying to do too much in my head. Let me write this down. 2t. All right, so there we go. This is y prime. Plug t equals to 0 into that, we get what? We get C2. So you guys told me that this was given to me by the audience, 2. So 2 is equal to plug in 0. Sine of 0 is 0, cosine of 0 is 1, so I get C2 plus nothing. So apparently, these give us that C1 is minus 1, and C2 is equal to 2. So therefore, I get y is equal to like minus cosine of t plus, yeah, thank you, plus 2 sine t plus t squared plus 1. And that would be the solution to the initial value problem, y prime prime plus y equals to t squared plus 3, subject the initial conditions y of 0 is 0, y prime of 0 is 2. But unless I give you initial conditions, you should expect there's a C1 and a C2 in the answer for a second order problem, right? Third order problem, we had how many constants? 3, and so forth. All right, so far so good. This naive method is working pretty well. Let's break it. Because it can be broken. And it can be broken in a lot of different ways. Yep, both of the examples so far, naive method. It's naive in the way we're forming the particular solution. What's that? I mean, I don't know what the official name would be. I guess the official name is always undetermined coefficients. It's just that the full undetermined coefficients, if you look in the book, it's like this theorem that's like 2/3 of a page with 13 different cases. I'm going to show you a method that you can calculate the particular solution on the basis of the knowledge we already learned last time. All right? So here's an example 5. Suppose I'm up against y prime prime plus, let's say, minus y is equal to e to the t plus o t. All right? So first of all, my homogeneous solution, I've got lambda squared minus 1 equals to 0. Therefore, lambda plus or minus 1 tells me my homogeneous solution looks like C1 e to the t plus C2 e to the minus t. All right. So far, so good? Great. Now, look over here. This is my forcing function. So that suggests I make my particular solution a e to the t plus bt plus c. That's the naive guess. If I look at this and I think about derivatives of it, that's everything that's possible from that kind of thing, right? Now differentiate. A e to the t plus b. Differentiate a second time. Yp prime prime is a e to the t. 0. Plug it in. What do we get? Mm-hmm.
A e to the t minus b t minus c.
Minus. Oh, minus bt minus. Thank you. Distribute the negative. Very good advice. Like that, and then that's all equal to what?
E to the t plus t.
E to the t plus t. All right. So here's the thing. If you look at this piece, right? And if you look at this piece, that's okay. We can make that match, right? We can make this match that. We just do what? Like, if I make b equals to minus 1 and c equals to 0, these match. Do you agree? That part's okay. That part's okay. But what about this? And this? They cancel. You cannot produce e to the t. You cannot produce e to the t over there with that, right? The naive guess fails. It doesn't work. We cannot produce this term. So how do we fix this? We fix this with what's called the method of annihilators. All right? So I'm going to show you how the method of annihilators works. The purpose of the method of annihilators is to propose the correct form for the particular solution. So here, we have d squared minus 1 acting on y equals to e to the t plus t. An annihilator for a function is a smooth differential operator, let's say, all right, which sends the function to 0. So I usually use a capital A for that. I'm sorry if there's any confusion. Like, the A I use for coefficients here is in no way related to the capital A I use for annihilator. I'm sorry, I think it's the book's fault. But if you want, we could use K for the annihilator, K for killing. Would you like? Should we change it to K for killing it? I've used A for all of my previous solutions, so it might get confusing if I just start using K now. I'm going to stick with A for now, but I really do want to change it to K for... Oh no, A is for annihilation. That even sounds better. Anyway, so my question to you guys, I want A to act on e to the t plus t, and I want it to be equal to 0. What differential operator should I put there? I'll do the easy part. D squared. Well, d squared will do this. D squared on t will be what? 0, right? Twice differentiate 0. E's a gone. How can I kill e to the t? No. I wanted to send it to 0. I'm not looking for the inverse function. Inverse function, it just has a child with natural log, and it lives on as the constant function t. We want to erase its history and progeny. Devote it to destruction. Don't be like Saul. Don't leave the oxen. No, that would still leave 1, which would be, that's not what we want. No, we want it. I want a differential operator. Fill in the blanks. That when I feed it e to the t, I get 0. I'll start you out. Derivative. All right, let me jog your memory. Last class we proved that d minus lambda acting on e to the lambda t is equal to 0. Okay, we did it with x. There's what it looks like with t. d minus 1. Bingo. So if d minus 1 kills the exponential and d squared kills t, if I want to kill both at the same time, I make my annihilator d squared times d minus 1. All right, that's the annihilator. So then what I do then here is I annihilate the differential equation. So I do d squared times d minus 1 times d squared minus 1 acting on y is equal to d squared times d minus 1 acting on e to the t plus t, right? So I'm just letting a act on both sides. This is a, right? This is L in our usual notation. So what do I got? What's the whole point of this? This is what? 0, right. Now, if you don't mind, I'm going to erase the derivation of the annihilator stuff, if that's okay. All right. I'm going to work up here where you guys can see me. So what we got? We've got d squared times d minus 1. That was the annihilator. I'm going to factor that. D squared minus 1 becomes d minus 1 times d plus 1, acting on y equals to 0. Wait a second. We know how to solve that. That's a homogeneous problem, isn't it? Get what I'm saying? Annihilating the differential equation changes the non-homogeneous problem to a homogeneous problem which we already know how to solve. Look at this. The d minus 1 is combines, right? So we get a d squared times d minus 1 squared times d plus 1 acting on y equals to 0. This tells me that the solution has the form like c1 plus c2t plus c3 e to the t plus c4 t e to the t plus c5 e to the minus t. All right? Now the way this works is contained in that list, there are two kinds of things. There are the terms which we already know are just sent to 0 by the original differential equation, by the original operator L. Those are the homogeneous solution. Let me circle those in green. What are they? Like this piece, right? And this piece, those are already present in the homogeneous solution. This has to happen because part of this differential equation we're solving is formed from L, and whatever L sends to 0 is what we call the homogeneous solution. Whatever's left is the correct form for the particular solution in this method. So this prompts me to make not the naive guess anymore, but the proper guess that the particular solution should have the form A plus BT plus CT e to the t. This is the correct form for the particular solution.
And for that, you were looking at the d squared as well as the d plus
I have to look at the A times L, the annihilator times L. Let's see if it works.
Well, I mean, in terms of the particular solution, like when you're specifying the particular solution,
It's whatever piece is not the homogeneous. The homogeneous here has e to the t and e to the minus t. So whatever else is there, that must be the part that's the particular. So we can try it out. We have, yp is equal to a plus bt plus ct e to the t. What happens when we differentiate it one time? We got b plus c e to the t plus ct e to the t. Why do I have two terms there? Right, that's the product rule, right? Product rule gets a lot of attention in this course, doesn't it? It's here. So then what? Probably need to calculate a second derivative. What's that? So we got yp prime prime is c e to the t plus c e to the t ct e to the t. All right. Now let's put it all together. We're supposed to look at what? Y prime prime minus yp equals to e to the t plus t. All right. Put that in. I've got what? I've got 2 c e to the t plus ct e to the t minus yp, which I'm going to put some parentheses here. Parentheses are your friend. Now you told me last time to distribute the minus, and that's good advice. But what if I got distracted mid-calculation? If I put the parentheses there, that helps me to remind myself to distribute that minus, which is so critical, really critical step. Okay, so what happens is, okay, so there's still cancellation, right? This and this be canceling, fine, but we're still left with exponential terms, right? So we've got from e to the t, if you look at the two sides, we've got 2c on the left-hand side, and I've got 1 over here. So I've got 2c equals to 1. Let's see here, from t-type terms, what do I got? Minus b. Anything else? Nope. Over here? 1, right? And from constant terms, what do I got? Minus a. And over there, 0, right? So you can solve these. My undetermined coefficients are no longer undetermined. They're in fact a half, minus 1, and apparently 0. And let's put it all together. The general solution then is c1 e to the t plus c2 e to the minus t plus 1/2 t e to the t minus t. B was minus 1? Yeah, minus t. And there you go. So I used to teach this to Calculus 2. Not here, but I started teaching calculus at NC State when I was a graduate student there. And this was expected of us to teach this to engineers there because the engineering department wanted them to have second-order non-homogeneous equations understood at that point in their education for their engineering courses. And so there, I wouldn't do operators. The way I would explain it for them is that the particular solution has to be modified whenever there's a quote-unquote overlap between the homogeneous solution and what you might call the naive solution. So here, there's an overlap. See this? I have e to the t in the homogeneous solution. And in the naive solution, up here, right, I have an e to the t. There's an overlap there. So that part of the solution needs to be modified by multiplying a t. All right? That was the method I taught them. Just simply that. If you look for an overlap, term with an overlap, multiply by t. But But then it gets fussy because you're not always supposed to multiply the whole naive solution by t. The question is, which part of the naive solution should you multiply by t, right? Well, the answer to that question is ultimately given by the method of annihilators. The method of annihilators tells us exactly where to put a t, or sometimes even a t squared if there's too much overlap, all right? So so a question that you're going to have pretty soon, once you see what I'm doing, is how on earth do you figure out what the annihilator is for a given function, right? I mean, maybe you already have that feeling. You know? So what I want to do in the next couple of examples is stop short of solving it all the way. Solving it all the way, doing this algebra, takes a lot of time for more sticky examples. And what you need to see more of at the moment is how to set up the method. All right, so let's do some more examples. Example 6. So let me just give a big picture before I get into the example 6, though. Big picture. Here it is. To find form of yp for L of y equals to f. Step number 1, factor. Well, this isn't really step number 1, my bad. Find annihilator such that AF is equal to 0. So here I'm saying A is some polynomial, let's say G. Oh man, thank you. G of D. Thank you. Step number 2 is to annihilate L of y equals to f. Basically, we get ALY equals to AF, right? Which is by assumption 0. Step number 3, maybe step number 3 has step, I don't know. Step number 3, find general solution to ALY equals to 0 and identify which part is not the homogeneous part. Whatever that is, call it yp. And that's how to set up yp. Now, past that point, like step 4 in this, to actually solve the problem, you have to plug yp in, work it out, and undetermine the coefficients. A lot of times in the test, I'll have two kinds of problems. I have one kind of problem, which is just solve the differential equation, in which case the final solution should only have as many constants as the order of the problem. If it's a second order problem, you should only have a C1 and C2, right? However, if I just say set up the form of the particular solution, then you don't actually have to plug it in and work them out. All right? So let's work an example like that. Example 6. Here we go. So suppose we have something like y prime prime plus y prime equals to, I don't know, t squared. That's probably good. Let's go with that. Let's keep the example a little bit simpler this time. So first of all, I look at this, I've got d squared plus d, right, acting on y equals to t squared. What should I make my annihilator this time? What will annihilate t squared? I heard a third derivative. So d cubed acting on t squared is equal to 0. Very good. You got it. So then I annihilate this differential equation. I get d cubed. This factors to d times d plus 1, right? And that's equal to 0. group any common factors. So we have d to the fourth times d plus 1, y equals to 0. So that tells me my solution has the form y equals c1 plus c2t plus c3t squared plus c4t cubed plus c5 e to the minus t. It might have, so like here's the thing, guys, I forget sometimes. It's probably good practice at the start of these problems just to write down what the homogeneous solution is, because you're going to need to know it later in order to finish the thought. So what's the homogeneous solution here? We can kind of see it from down here, right? Lambda equals to either 0 or minus 1, right? So the homogeneous solution is what, like c1 plus c2 e to the minus t, right? Because this gives me lambda squared plus lambda equals to lambda times lambda plus 1 equals to 0. So that's my homogeneous solution, okay? So in view of that, that means, we'll look at it, right? So the first piece here and the last piece, the first and the last, are actually the homogeneous solution in this particular case. So what should I make my particular solution here? This business right here, this is what I should do. See, this right here should be my yp. So I would form yp as like a t cubed plus b t squared plus ct. What's the naive guess, by the way, in this context? It would have been what? Just, yeah, at squared plus bt plus c would have been the naive guess, right? So what's happened here is we've taken the naive guess and we've multiplied by t. That's what the annihilator method told us to do. And then to solve this problem, you have to take the derivative, take the second derivative, plug it in. You'll find values of a, b, and c which make it work, all right? You guys can do that. Yep. Oh, okay. Let's do another. The rest of this right here, what was it? Use method of annihilators to formulate yp. Or fill in the blank. There is something else. This method of annihilators is not foolproof. There are examples it doesn't work for. All right? We'll get to that. We'll get to that. Here's another example. Example 7. Set up yp, but do not determine a, b, c, etc. I usually put this in all caps when I give that instruction in the test. Ignore it at your own peril. Because every time I put a question like this, there's always about like 10% of the students who don't see the do not determine, and they just start trying to determine it. But I said specifically, do not determine, which I'm trying to say, you don't have to do the rest of what's required, namely to differentiate it again, plug it back in here, and work out the values for a, b, and c. All right? Okay, so here's the problem. Y prime prime plus 2y prime plus 2y equal to let us say t cosine t. Plus, tell you what, let me not make it too hard. Let me keep it simple-ish. Let me just make it e to the minus t cosine t. There we go. That should be enough trouble. Okay, so first order of business, this right here gives me lambda squared plus 2 lambda plus 2, which by the way is lambda plus 1 squared plus 1. If you set that equal to 0, we get lambda is minus 1 plus or minus I. Therefore, my homogeneous solution has the form C1 e to the minus t cos t plus C2 e to the minus t sine t. So at this point, you should realize, uh-oh, we're in for trouble. Why?
Because we only have two.
What do you see in the homogeneous solution? If you believe me. I see a negative t cosine t. What is the forcing function? Negative t cosine t. So they overlap. This is the place, again, where the naive method is going to fail. All right? So how do we annihilate? The funny thing about this is the question of how to annihilate the forcing function. It's right in front of you. It's staring you in the face. What is annihilator here? What is the annihilator? How about this? It's right here, right? D squared plus 2d plus 2 acting on e to the minus t cosine t is 0, isn't it? Isn't that the whole point of the homogeneous solution? If I plug these two functions into the differential equation, they spit back 0 at us. So in this case, I can actually use L is equal to A. All right? So this is a perfectly good choice for my annihilator. So essentially, I take this differential equation, right, and I operate by A, which is this, and I get d squared plus, I meant to put a 2d here if you guys are wondering. There's a 2 there in my mind, but not on the board. Maybe that's why you guys are confused. 2d plus d squared plus 2d plus 2. But I got 2 of them, so square it. Acting on y is equal to 0, which is to say d plus 1 quantity squared plus 1 squared acting on y equals to 0. So here we have a complex root of minus 1 plus or minus I repeated. What's my solution to the annihilated problem? Well, it is y is equal to c1 e to the minus t cos t plus c2 e to the minus t sine t plus c3t e to the minus t cos t plus c4t e to the minus t sine t. So the first part of that is the what? The first part of that there is the homogeneous solution, right? And this over here turns out is the correct form for yp. Yp, we're going to do like at e to the minus t cos t plus bt e to the minus t